Good afternoon, everyone. My name is Youngjun Kim. I'm part of TU Power Group. I'm here to present our project, Smart AC Power Consumption Meter. So this is the abstract. So we're going to build a smart AC power consumption to monitor energy usage, energy consumption. This is the team member of our group. Eamon does the power analyst and the communications. William does signal processing and programming. And I do system hardware implementation, not the senior system programming. And our advisor, Dr. Higgins, and co-advisor, Dr. Biswas. So, what are smart meters? They are the devices that monitor home energy usage and it helps to understand the energy consumption. And they use the base tool from the utility providers, and it can help to reduce energy consumption, cost, even control certain devices. So, these are the energy monitoring devices in the market. Is cost and consumer rating for e-monitor, energy monitor, e-monitor, energy monitor service, Watson power monitor, and blue line power cost monitor, and kilowatt easy electricity monitor. The kilowatt monitor displays the energy power consumption, but it doesn't store the data. E-monitor is really complicated to set up, so without the electrician, we can set this device up. So our primary goals are raise awareness by education, environmental sustainability by reducing carbon footprints, and accessible cost by providing affordable energy system. So this is the block diagram of our whole system. So we have 3 stages: input stage, process stage, and output stage. So we have 5 technical design constraints: power, wireless communication, data measurements and accuracy, display output data, power factor calculation. We have 5 non-technical design constraints: economic, which is cost, manufacturability, size and dimensions, social media, which is sharing, sustainability, which is reliability, and safety, which is radio frequency signals. So now I'm going to talk about the input stage. This is the block diagram of the input stage. We have Hall effect current sensor with level shifting, and voltage transformer and level shifting, and microcontroller and XV transceiver. Current sensor. We are going to Hall effect current sensor. We are going to use the Hall effect current sensor. We will obtain the analog signal by converting current to equivalent voltage. So these are the equation of the converting and the level shifting. So I is for current. The voltage V out is for equivalent voltage. The voltage transformer will step down the voltage from 220 VRMS to 5 VRMS and transmit the analog signal to the microcontroller. And the voltage signal will be level shifted to account for the operating range of microcontroller, which is 0 to 5 volts. this is the equation of transport current ratio. So this is the voltage level shifter simulation. The voltage level shifter will offset the original voltage signal to 0 to 5 volt, which will allow the microcontroller to handle the input signal. So this red one is showing the original signal, and the blue one is showing the offset above the 0. So this is the calculation to get the power factor. So we need to acquire instantaneous voltage and current samples. Then calculate the average power and average apparent power. Then we calculate the power factor. So these two are equation of to get the Vrms, Irms. Then we can calculate the apparent power and average power. Then we can finally get the power factor. So this is the first slide is showing the result of the previous calculation. It's showing the average power, real power, reactive power, apparent power, and power factor. We got the power factor about 0.8. And the second plot is showing the reconstructed signal of the voltage and current samples. And these two horizontal points is showing the difference, showing the phase difference, which is 34.27. When you calculate the cosine of theta, you can get the power factor, which is about 0.8. And when the power factor closer the power factor get to the 1, you will get the less power loss. So, and we just measure the power factor, but we just measure the power factor. This is a simulation for the point-to-point communication. The first picture is showing the communication between XCTU and Arduino. So these red words are from the Arduino, and these blue words are from XCTU. And this picture is showing the circuit to connect the XP to the Arduino. So in input stage, we use the Arduino Uno for microcontroller. So it samples the analog signal at the sampling frequency, which is 1,200 samples per second. And the AD converter will convert the voltage and current signal to digital data. And also calculate the real power, reactive power, apparent power, and power factor. And the calculated data will be sent to the base station via XP transceiver every minute. So XP transceiver will transmit and receive all data via Zigbee Wi-Fi protocol. The radio frequency signal will operate at 2.4 GHz at 1 mW. The signal range is 300 feet. Baud rate, which is bit stream rate, will be set to 9,600. So I'm going to talk about the process stage. So in process stage, this is the block diagram of process stage. We have XP transceiver, microcontroller, and SD memory card. In processing stage, we use the Arduino Mega for the microcontroller. So it performs the summation of power and reactive power and apparent power. And then it also performs the comparison of the data over time. And all of data will be displayed on the website, and you will store it in SD memory card. So this is the system budget. We estimate the system budget $327. This is the remaining schedule. So me and Eamon will do power supply hardware simulation, and William will do wireless communication test, and Jimmy is going to do signal digitization and accuracy. So our project challenges are obtaining the current and voltage signal at the input state and perform accurate calculations, powering the entire system. Our project risk mitigations involve: 1, transferring data to the website. It will be reduced by minimized bit stream and data transfer duration. 2, miscalculation due to signal conditioning. It will be reduced by simulate the input data to ensure accurate calculations. 3, handling high voltage lines. It will be reduced by following safety procedure in lab. These are the goals for Senior Design 1 and Senior Design 2. In Senior Design 1, we do complete project analysis and the simulation, completion of the design document, start ordering the components for next semester, and beginning construction of the first prototype. In Senior Design 2, we'll do revised design documentation, implement the design scope, adjust the design criteria upon test data acquired, and finalize the working type. So these are our references. Questions?
Questions?
You basically send the samples from the measuring station to a process units, right?
Yes.
1,200 samples per second.
12, no, just
1,200
1,200 samples per second.
Do you know how much data rate you're going to send it over?
For the
How many bits per sample?
between the input state and the process state, we send only every 60 seconds. We're not gonna send every millisecond or something. Every 60 seconds we send it over.
But
The sample rate is the sample to
1,200 samples per minute. It's not per second, right?
No, that is for the input state to acquire the signal. That we set the sample up to 1,200
But do you
samples
know
per second.
XP the transmission rate?
The bit stream rate?
Yeah, transmission rate.
We're set at 9,600.
9,600.
That's the standard value.
Baud rate, which is
That's a BPS,
Yes.
bits per
bit stream
second.
rate.
Did you calculate? For 300 feet, the probably even less than that, right? Because app signal degradation.
I think if you go back to the first slide where you had your block diagram and you explained where the data is being processed and what's being processed in each block. Right, the next one, there. In the input stage, what you're doing, and then in the process stage, what you're doing.
Okay. Yeah, this input stage, we basically get the signal and the level shifted, and we calculate the in microcontroller the to calculate the data, we will send
So
to
what's the
the.
distance between input stage and process stage?
Yeah.
What's the distance? Up to 300 feet?
We haven't,
Well,
ba-
we haven't, it will depend on the loads, because we'll have different loads. So we have a base station center somewhere, like in your house, and then wherever the load is, it shouldn't be too far away from the base station. It's not gonna be 300 feet, so, but we haven't tested it yet because we don't have the loads.
the XP that we're going to use, the transceiver we're going to be using, it trans up to 300 feet.
Okay.
This is for home application, right?
Yes.
So within the home, 300 feet is too much, right?
It's more than enough, and that's basically like the lower end of the.
So maybe we should really just modify this because, you know, like, a house most likely, the width is like 60 feet or something.
But how often is data going to go across from the input stage microcontroller to the process stage microcontroller?
Every 60 seconds.
Calculate how
60
much,
seconds.
how many
Every
bits
60, every
will
60
generate.
seconds.
Every 60 seconds.
So once a minute, that's going to go over the ZigBee.
It's 1,200 samples.
But that's all getting processed in the front end.
It's a process the input stage.
Yes.
Oh, okay. I thought it's
That's
process
what
stage.
they didn't
Okay.
explain why.
Okay, all right, that makes sense. Okay.
More questions? Go ahead.
You may have mentioned, I came in a couple minutes late. What is the objective of this, you developing this system, and does the operation of it meet your objectives?
Well, the thing is, like, our research basically shows that in terms of in the U.S., there's a lot of demand for energy use, and with that, there's, in terms of our production, it's basically low. So we're trying to basically create a bridge in between production and demand, and also with that, also reduce waste. Okay. Also trying to basically go green, so to speak, in terms of power losses. We know, for example, like in every home, there's a lot of components that everybody plugged in there, might be plugged in, but they're not being used. Okay, so it's kind of like phantom loads. So you're not aware of how much energy that component is basically zapping. Okay, so to do that, we're trying to show that you can basically monitor what's being used, okay, and whatever's not being used too at the same time. That's basically our idea.
Okay, and so I guess what you're saying is, once the homeowner reviews the information,
They can basically educate themselves on, okay, you know what, let me turn this off or take this off, and look at and we know the homeowners are only interested in dollar value. And if you want to reduce your dollar value, you have to basically understand what's going on in your home in terms of components. So this will kind of like help you kind of like.
Now, does this get installed at the line side of the service into the house, or the load side
From the load side. There's the line side, we figured not to get into that because that's working with high voltage power, and that's something where you have to definitely use an electrician to basically install that.
Now, is it interfaced with each individual load bank, or is it, if you have multiple, let's say you have a 200 amp panel with 15 breakers, do you just pick which ones you want, or it's?
We're not connected to a panel. That's basically to your AC outlet.
Okay, so it's specific to
Yes.
an individual, a toaster
Yeah.
or
Yes.
a microwave or something?
Right now, the prototype is basically geared towards one component, but we figured that we can basically measure up to 4 at the most for now.
But do you think it would be useful in developing it so that it can be, because if I'm only plugging it into the toaster, well, okay, I know that. So is it meant to, if it's labor intensive for the person that's using it to just keep going throughout the house, plugging it in, do you think you get more, through research and development, more value out of it if you can develop it so that it can get installed in one spot and be able to monitor everything.
Yeah, that would definitely be a plus, but once again, I mean, with that, it's a little bit more difficult, so to speak, and like I said, you definitely need someone who's like definitely an electrician to basically have, because you have two lines coming to your home, and with that, you can. Some research that you have to basically use like a current transducer and basically clamp it to those two lines, and from there you can basically read what the whole home is basically using at that point. But our focus is not just on that, but it would be much more.
Okay, we have only 1 second left, okay? And then you can talk outside. Okay? Now, one quick question. How many meters you can accommodate at the same time? Like, you are designing 1 meter right now.
Yes.
But if you have 4 appliances, can you accommodate 4 appliances?
Yeah, 4, yeah.
Okay, can also you reference that to the overall power consumption of the house? Like you put a meter near the main parts, main lines? Because like if you tell me this takes like 1 kilowatt, for example,
Yes.
I need to know exactly what is the house is consuming at this particular instant.
We figure like through calculation, and once the bill comes, so to speak, you can basically.
No, I mean
compare
instantaneously,
overall.
not really do it for the bill. Right now,
Instantaneously?
yeah, right now, if this is taking 1 kilowatt, what is the power
Power being.
taken from the supply, from
Yeah.
the PP&L or whatever?
Yes.
Can you just put a meter there, right?
Yes.
Okay, thank you.